Okay, welcome everyone to the second lecture of Thibault's, I think, fourth lecture. We just started a bit late, so sorry about that.
Right. Thank you. Thanks for being here. So let me start with a quick recap of the last lecture. So last time I argued that a large Hamiltonian system, so large system involving a large number of interacting particles, would generally relax to equilibrium at large time. And that's what they will do for a large class of interaction potential. And at equilibrium, those systems are characterized by the so-called Gibbs measure, which I've written here. And this, again, is for generic interaction potential. It's the only invariant measure in 1D. So here, the E, N, and P represent quantities that are conserved by the Hamiltonian dynamics, and the parameters beta, mu, and nu here are Lagrange parameters to ensure that those conserved quantities have the correct value. And if the system is inhomogeneous, then we assume that there is some propagation of local equilibria, meaning that the Lagrange parameters beta, mu, and nu now depend on space and time slowly throughout the system. And we describe their propagation through those macroscopic conservation laws here. And the main idea behind this assumption is the fact that we observed that in real classical fluids, typically the Lagrange parameters, the beta, the mu, and the nu, they vary over distances that are typically of order 10 to the minus 4 meters, whereas the interparticle distance is typically of order 10 to the minus 7 or 10 to the minus 10. So you can construct fluid cells which contain a few thousands of particles, let's say, and then you assume that those fluid cells are locally at equilibrium, that they are well described by the Gibbs measure, which Lagrange parameters are no depending on x and t, okay, corresponding to the fluid cell, which brings us to the hydrodynamic approximation, the fact that the average of an observable at xt can be well approximated by the average of that same observable, but within this, the fluid cells, the fluid cell of coordinate xt. So it's this average is equal to its sensible average, but for with respect to Lagrange parameters beta, mu, nu of xt. Okay. And those macroscopic conservation laws that describe the propagation of local equilibria, as I said last time, they are system of hydrodynamic type. And I ended last lecture by talking a bit about the systems, discussing their properties, and in which conditions we can solve them via other options for. Okay. So that was for last lecture. And to draw a bridge between last lecture and this one, I want to talk about the Fermi-Pasta-Ulam single problem. Right? So that's very notable for several reasons. Maybe the first one, it was because it was one of, if not the first, molecular dynamics simulation. So it was realized in 1953 of the then new supercomputer Maniac 1. And the authors here were looking for a way to test this new supercomputer and to understand what this new kind of doing simulations could bring to the table. Okay. And so they decided to look at how large Hamiltonian system would relax to equilibrium. And they wanted in particular to look at Hamiltonian systems that featured nonlinear forces, systems for which they did not have closed analytic solutions, so that they could really showcase the power of this new approach. Okay, so they were looking at chains of particles, 64 at most at the time, that interact with the nearest neighbor in this way for different types of interaction potential V. And the supercomputer would then solve these equations of motion. Yeah. And Fermi's main hypothesis behind that was that any Hamiltonian system which features nonlinear forces should be ergodic, that interaction would yield a good mixing, and that eventually the system would always relax to equilibrium. So they started looking at this kind of potential here, which is called the alpha PUT model, alpha being here the strength of the nonlinear force. And they started looking at that because it's very simple, and also because it can be a good approximation of more general potentials in the limit of small displacement. They started with this alpha PUT model, and they decided to look at initial conditions where they arrange the particles so that they form one single sine wave. So here I put a small animation. So in purple, you have the dynamics of a linear wave where alpha is equal to 0, and in black you have the nonlinear wave, alpha non-zero. And you can see that quickly the nonlinear chain deviates from the linear one. So you start with a wave that breaks, that regularizes into a dispersive shock wave where you have a trailing edge followed by oscillations, and then because you have periodic boundary conditions, the oscillation bumps back and forth and start to interact non-linearly in a fairly complicated way, right? And according to Ulam, Fermi was really the main driving force behind this project, and Fermi expected to see somalization, so which is an ergodic process in which your system essentially forgets about its initial condition, becomes more or less random, and eventually relaxes to equilibrium. If you are at equilibrium, then it means that your system is well described by the Gibbs measure, which in turn implies that all modes of vibration on average should be equally excited. So this is known as the equipartition theorem, which is an important result of statistical mechanics that I have not talked about last time. But in fact, that's not what they observed. So this figure is taken from the original paper from 55.
And who is this last person? T.
It's Tsingo. It's
he was not author of that paper.
No, she was not author.
She, I didn't know. Yeah.
Yeah, she was not author. She was in the acknowledgements, but she was the one who did all the simulations.
I see.
Yeah.
Ah.
So retroactively, she was included. Yeah. And the paper was published in 55. The simulations were made in 53, but the publication got delayed because Fermi died in 54. So that's why there's a 2-year gap between these two. And yeah, so that's from this paper. And what they observed is that they start with all the energy in the first mode. That's the mode. They started with a single sine wave here. And with time, gradually the energy of mode 3, 4, 5 would increase. Okay, so that's what was to be expected. But in fact, after a while, energy sharing stops. And in practice, only the first 5 or so modes are significantly excited, and they are not excited in equal parts either. And on top of that, they observed that after a very long period of time, so much larger, several thousands of times larger than the period of the linear wave, the system would almost go back to its initial state, right? So instead of summarization, what they observed was a complicated quasi-periodic behavior. Okay. And the explanation for the behavior would come much later, and it's because the FPUT model is actually very close to integrability. In fact, the alpha FPUT model in its continuous limit can be very well approximated by the Korteweg-Jeffreys equation, which is itself integrable. But why is this important? right? Why is integrability important here? And to give you an answer of this, I will try to give you a flavor. Here is this introduction, and it's because thermalization, in the sense of equipartition of energy, can be related to ergodicity. So if you consider your initial condition as a single point in your phase space, then if you assume that your nonlinear dynamics is ergodic, as Fermi did, then it means that the trajectory of this initial phase point should be dense everywhere in the phase space, right? But if you do this, it means that then over large periods of time, on average, all modes of vibrations should be excited because you are exploring the phase space equally, every part of the phase space equally. Yes.
With modern computers, they find that it thermalizes.
Yeah, over very, very.
Because it's not exactly.
It's not exactly integrable, but it's very close. Yeah. Yeah.
But so I mean, I still have energy conservation, right?
Mhm.
So it is not possible that in the end, all modes are excited. Like,
No, it's not all modes are excited at the same time. It's on average, all modes are excited equally. So it means that you will explore the phase space and you will.
like the energy per mode should be constant like this. But like if I mean the high oscillation modes will have high energy, right? So you expect something like that the occupation goes down.
No, not if your system is perfectly ergodic, because you will go to parts of the phase space where you have very high oscillation. You will stay there for a bit, and then you will go somewhere else. And over large periods of time, on average, you should excite all modes equal. Right. So yeah, let me give you a quick illustration of this. So, for example, you can look at the kick throttle for an ergodic system. So it corresponds to a particle on a circle that moves freely, but is periodically kicked, changing its momentum by a force that depends on where the particle is. So it's Hamiltonian is something like that. It's E squared plus V of x from delta times okay. So if I draw the phase space for it, so it's periodic in x, right? Because I'm not the circle.
But here is energy is not conserved.
No, here the energy is not conserved, precisely. And often we also consider it's periodic in momentum because what matters is where the particle is when it gets kicked. So if I draw the trajectory, I take here, so it moves freely, then it gets kicked, so it moves freely, then it gets kicked, and moves freely, then gets kicked, etc. And eventually you will explore the whole phase space over a very large period of time. Okay, but instead, if you look at the harmonic oscillator, right? So here the energy is fixed indeed, and this fixed value of the energy specifies what really constrains, in fact, the trajectory of any initial phase point to stay on a specific orbit. Right? And if you had a second oscillator to your system, let's say your phase space is 4-dimensional, but now your dynamics is constrained on torus, and it's the same if you had a third or fourth, etc. Right. So basically, in general, a system is said to be Liouville integrable when you have n-dimensional phase space and n constant quantities, and you recover this kind of structure where the dynamics is constrained on torus. Right. So you don't explore the whole phase space. There's no mixing. So and that's why we say typically that integrability impedes thermalization. So I'll come back to that. So yes.
What happens if I do exactly the same experiment?
Yes.
With a different potential. Like,
okay, with a different potential, if you at least if you keep the same initial condition, you will have something roughly like that. So the large recurrence period might be different, but the general behavior will be the same. So they tried with what's called the beta FPUT model, where instead of having quadratic force, you have a cubic force, and they also have a linear force that saturates. And so they tried all this with the different kinds of rather long wave initial data, and they always see this.
So if I go to higher dimensions,
Okay.
Yeah. So the kind of question is like, how would it look like if I have like proper thermalization?
If you have thermalization.
How would this plot look like if I have proper thermalization?
Okay, so the thing is, if you have proper thermalization and you consider that you are really at very large times, I cannot say exactly what this plot would look like, but the idea is that if you integrate over this very large period of time, you will see that the energy is equally distributed among the nodes.
In any
In any basis, yeah.
with constraint that you are.
Yeah, of course.
On the show.
Of course, with the constraint that you are in the constant energy sequence, yeah. Right? So this lecture will be dedicated to integrability, and it will be dedicated to the tools that were developed to study classical integrable field theories. So I'll start by deriving the Korteweg-de equation from the alpha LPUT model. Then I'll talk a little bit about integrability and classical field theories and introduce some of the formalism. And then I'll show you how to construct simple but non-trivial solution to the KdV equation using inverse Catherine transform, and then how to construct explicitly n-soliton solution using the Dorfman transforms. Okay, so as I said, I'll start by deriving KdV from the alpha QT, for which I've written again the equations of motion here. Q being again the displacement of the particle, and F being the force associated with the potential of the alpha LPUT model. And as I said, I want to take the continuous limit of this, so I need to first introduce the lattice constant d, and I also introduce a function q, which interpolates between the q ends in such a way, right? So what's important here is that the dispersive effects that generates the dispersive shockwave you saw in the first movie are only due here to the fact that the lattice constant is non-zero. And the smaller the d is, the weaker these effects are. So this is important. Yeah. And the last thing I want to do is I want to consider initial condition in which I arrange my particles so as to form long waves of wavelength L that is much larger than the lattice constant d. So that's what FPUT did for the first simulation with a single sine wave. And if I do this, then it means that the displacement of particle n is very close to the displacement of particle n plus 1, which means that I can now expand the argument of the force here in this way up to fourth order in d. Okay. And then taking this expansion, putting it in the equations of motion, I end up with this nonlinear PDE in terms of Q up to terms of order 5 in D that I neglect, right? So here as you may notice, this equation only depends on the derivatives of Q and not on Q itself. So typically it's rewritten in terms of a new variable V, which is defined like that. And after some additional rescaling, we end up with what is called the bad Boussinesq equation. Yes, yes. So this terminology comes from McKean, but okay. So this equation is integrable.
Just, could you remind what is good Boolean equation?
Yes, the good Boolean equation is the same, but there's a minus here.
Okay.
Yeah. And I'll tell you why this one is bad. But yes, so so this equation is integrable, just like KDV. And in fact, in a way, we could stop there and study the integrability of this equation. But in fact, historically, that's not what happened, and that's not what we will do either. And there's two reasons for that. So the first one is that the Boolean equation is not as universal as the KDV equation. And the second reason, which is probably the most important, is that this equation exhibits severe short wave instability, in the sense that the solution for the bad Boolean equation for arbitrary initial condition generally does not exist for positive time. Okay, so that's why it calls the bad Boolean equation, or sometimes the ill-posed Boolean equation. So there's a good version that does not have this issue. But now the next step here is to derive KDV from this equation by, in a way, limiting ourselves to initial condition for which the dynamics of the Boolean equation exists. Okay. Right. So to do so, to avoid the short wave instability, and also to be consistent with our previous assumptions, we introduce two new slow variables, tau and psi here, which are related to x and t through some power of a parameter epsilon. Okay? And so those correspond to long waves in a moving frame that's moving with positive velocity of linear waves. Right? And what I mean here by long waves is compared, in fact, to the amplitude v here, which should be of order epsilon as well. Okay, right. Now, to stay in a regime where things remain interesting, we want to ensure that both the dispersion and the nonlinearity have the same order of magnitude. Otherwise, things become trivial, right? And so this fixes the values of the powers a and b of epsilon we take in our change of variable, right? By recalling again that v is over the epsilon. And then we can neglect terms of order epsilon 4. We can introduce one last new variable u in this way, integrate this equation once with respect to psi, and we finally end up with the coordinate degrees equation. Yeah. So this equation is integrable, and it does not have any issue of illipositiveness.
So a small amplitude approximation of this.
Yes, yes, exactly. But small amplitude for bad Boolean, if you, it also corresponds to long waves.
Long wave, small wave.
Yeah, exactly. So yeah, this again is integrable. It's also said to be universal in the sense that any system with a quadratic nonlinearity can be reduced to KDV in some limit. Okay. So it's been derived in many contexts, like water waves, magnetohydrodynamic waves, currents in electric line, plasma, etc. And even though the procedure we follow to derive it is a bit roundabout, in fact, it's been observed experimentally in all of these contexts, and it's known to capture many physically relevant phenomena. Right, so that's why it's been well studied in the last 50 to 60 years, and it's usually considered as a prototypical example of nonlinear dispersive integrable PDE. Okay, so just before I talk about the integrability of KDV, I want to talk a little bit about this old paper by Zabicki and Kulskau. Yes.
Sorry. So in the initial field,
yes.
Why did short wavelength with most of the game. I mean, did they prepare the system with a long wavelength?
Yes, the initial condition was an extremely long wavelength. It was just a single sine wave in a first mode.
Okay. So if you would have started with a much shorter wavelength, you would have found different options.
Yeah. Yeah, the really important part is that your initial condition is a long wave. Yeah. Right. And yeah, so in their paper in 65, Zabusky and Kruskal, I think there was the first one to relate FPUT to KDV, actually. And they then solved KDV numerically for the first time as well. And they started with this type of initial condition, a single sine wave again with periodic boundary condition. And they observed the formation of what's known as the dispersive shock wave here. And what they observed is that all these oscillations here, which are solitons, so I think they are the ones who coined the term as well. They observed that all those solitons, they would move at constant speed, which is proportional to the amplitude. And then because you have periodic boundary conditions, eventually they will start to interact non-linearly in a fairly complicated way. But the thing is, eventually, solitons separate, right? And what one of the key observations was that if two solitons separate, you cannot see here very clearly, but I'll show you another video later. When solitons separate, in fact, they emerge completely unaffected in size, shape, and velocity. It was a big deal at the time because it was the first example of a nonlinear process in which localized pulse did not scatter irreversibly. And so, yes, that's why there's no redistribution of energy among the solitons, so the collisions are just elastic, right? So there's no equipartition, there's no centralization, which again is a feature of integrability. Right. Okay, so what do we mean by integrability? And the thing is, even when it comes to integrable field theories, there's no one single unifying definition of what integrability is, and there are many ways to approach the issue. So here I will give you a few examples of properties that are typically associated with integrability or are sometimes used to define it. And so, for example, maybe the definition you've heard most often is the fact that integrable systems have an infinite number of conserved quantities that constrain the dynamics. But another definition is that an integrable system has to be bi-Hamiltonian, or that that means a zero-curvature representation, or lax representation, or tau function representation. Sometimes we say that a system is integrable if it is solvable via the inverse function.
Are these notions all equivalent?
No, that's the thing. That's the thing. Or yeah, the scattering can be reduced to two-body elastic process, like Zabusky plus Kruskal, so it turns interacting elastically. But in fact, yeah, as you said, those definitions or those properties are not all equivalent. So you have.
But it's only if you infinite number degrees of freedom.
Yes.
Classical definition by Louis.
It becomes a bit murky.
Yeah, it doesn't mean that it has an infinite number of constant quantities.
Yes. So I'll precise this in the next two slides. But yes, there's a more rigorous statement here. Yeah. Right. But yeah, not all these properties are equivalent. You have systems, for example, that have a zero-curvature representation, but don't have a lax representation. That's the case of sine Gordon, for example. Or you have systems that have a infinite number of constant quantities that are solvable via inverse scattering transform, but for which the scattering is not two-body reducible and for which there's no tau function representation. So that's a three-wave equation, which is still considered integrable anyway. So there's a lot of leeway here, and depending on who you're asking who you're asking, what they call integrable and the methods they use might vary significantly, in fact. Okay. But what's nice with KDV is that it has all those properties. Okay, so I'll take a little bit of time and talk about all of those to give you a broad overview of the field. So that's because, well, some formalisms are better suited to tackle certain problems, of course, but also maybe you will find parallels with what you do in your field with some of these approaches. And anyway, I think that if you want to delve deeper, ultimately, I think it's better that you know what exists, so that you can pick and choose what's the best entry point for you. Okay, so to set the stage, I'll start by talking a little bit about finite dimensional Hamiltonian system. And here, when I'm talking about dimensions, I'm talking about the dimensions of a phase space, not of the Greek space. Okay. So say I have an n particle system in 1D, then my phase space is R to the 2m, and each point of the phase space is identified by its Thibault coordinates QP or equivalently x. Okay. And what's really important here is that I've paired each QI with its associated PI, because they are the position and momentum of a single particle. And to encode this information, I've also introduced this antisymmetric matrix J called the symplectic form. And with that, I can define a Poisson bracket from the following bilinear map, which can be expressed in terms of either the symplectic form or of this sum here, which you may be more familiar with. Okay. So this is a usual Poisson bracket. It's symmetric. It has the Leibniz property. It satisfies the Jacobi identity, etc. So all the usual properties of Poisson brackets. And then, as you probably know, an Hamiltonian system is characterized by a function h called the Hamiltonian, which yields Hamilton's equation in terms of the Poisson bracket or in terms of the symplectic form. And this specifies the dynamics of the system. Right. And more generally, the dynamics of any observables, of any function of the phase space can be obtained through a Poisson bracket that involves the Hamiltonian. So, of course, if the Poisson bracket between f and h here is equal to 0, that means that the observable is invariant under the dynamics. Now, such a system is said to be Liouville integrable if there exists for two n-dimensional phase space, if there exist n independent functions f, such that the Poisson bracket of each pair is equal to 0. And typically we choose f1 is equal to h. So these observables are also invariant under the dynamics. So what we require for integrability, in fact, is a bit stronger than just having n conserved quantities. It's having n observables that commute. And here that's important because each of these observables can generate a vector field through an equation like that, by when you replace h with one of the f's here. And the vanishing of the Poisson bracket ensures that all those vector fields commute. So you see there's a lot of structure here in this, yes.
So independent, what does that have to do?
Linearly.
Linearly.
Yeah. Yeah. Right.
Okay.
No, but that's a function independent.
Yeah.
H square is not a new one.
Yeah, yeah, yeah.
Ah, okay.
Yeah, h squared. Yeah. Also, yeah. No, you're right. Yeah, h squared doesn't come. Yeah, right. Sorry.
And it should be smooth, it should be nice function.
Yeah. Yeah.
Yeah.
The conserved quantity is just that it commutes with h, right? So if it commutes with h, if I have two different functions that commute with h, doesn't that mean they commute with each other?
No, they don't necessarily commute with each other. So it's a bit stronger than that. Yeah. What you need. Right. Any more questions? No. So you do have a lot of structure in these systems, and in particular, for any fixed values of all those commuting observables, you can construct a manifold MC like that here. And Arnold-Lewin theorem tells you that this manifold is smooth, that it's invariant under the dynamics, obviously, because all the conserved quantities are conserved, and also that it is hypermorphic to an n-dimensional torus. And on top of that, it tells you that there is a canonical transformation to the so-called action angle variables that trivializes the dynamics. And here, what we mean by that is that the action coordinates, here the i's are always constant, and the angles coordinates, the thetas, are always just evolve linearly. Okay. So here we recover the fact that integrability really constrains the dynamics into a specific region MC of the phase space, and also that it provides a way to obtain explicit solution using this canonical transformation. Right. Okay, so this was finite dimensional integrable systems. So finite dimensional Hamiltonian systems deal with systems of ODEs, but you can also see a PDE as a system of ODE of infinite size, right? Where the space variable x, each value of the space variable x can be seen as a continuous index, right? So of course, it's a bit more central than that, because one case is countable, the other is not, but right, that's the gist of it. More or less, yes. Right. So yeah, instead of the coordinates of the phase space x, you consider the KdV wave field u. Instead of observables as functions of phase space, you consider functionals of u of some appropriate function space. So let's say a Schwarz space if you're considering soliton solutions, for example. And then you also have to modify your Poisson bracket in such a way where now the curly J is an antisymmetric operator. So now I'll try to apply those previous notions about integrable Hamiltonian systems to KdV. And the first thing I need to mention is that KdV is a bi-Hamiltonian system, in the sense that the KdV dynamics can be obtained from two pairs of J's and H, which I've written here. And commonly, this set J2H2 is more commonly used because this Hamiltonian corresponds to what is traditionally thought of the energy of the KdV waves in physics, whereas this Hamiltonian is a momentum. So KdV is Hamiltonian, but it's also integrable, and that's something we can already see from that. And the way to see this is to notice that this bi-Hamiltonian structure implies this relation between the two H's, right? And from this relation, we can recursively construct an infinite set of HNs, okay? And then it's rather easy to show that all of these HNs Poisson commute. Okay?
With respect to both?
With respect to the J2 bracket.
With respect to one.
Yeah. Right.
So the J1 is not integral.
Yes. Let me see. No, probably it should also commute with respect to the J1. I've only tried with the J2, but probably the J1 should work as well. Yeah.
So they're fully doable.
Yeah.
So is KdV bi-Hamiltonian or
Yeah.
infinite Hamiltonian?
No, it's bi-Hamiltonian.
Yeah, only two.
Infinite means what?
No. Okay, so you have an infinite number of conserved quantities, but you don't have. You cannot use H5, let's say, to generate the KdV dynamics.
Suffices to go one.
To be Hamiltonian, you need one. But this one is bi-Hamiltonian because you have two, and the question was is it a multi-Hamiltonian? And this, I don't think so, but I'm not completely sure, so I don't want to.
But I don't see any reason.
Yeah, exactly. Right.
Yes, so is that the definition of HN plus one?
Yes, that's the definition of HN plus one. You construct them recursively from that. Yes.
Like when you have a finite dimension integrable model, do you also have two Hamiltonians?
Not that I know of.
Is it something that's only possible in infinite?
I think so, yeah. Well, the thing is, the simplex form in finite dimensional model, typically it's prescribed, whereas here you have freedom on which kind of, yeah. That's, I think that's the main thing, yeah. So again, you have an infinite number of dimensions, you have an infinite set of conserved quantities, but right, is that enough? Because the set of HNs is countable, the number of dimensions is not, right? So there might be a problem here, but in fact for KDV there is not, because this set is complete, and you recover some infinite version of the Arnold-Liouville theorem where you have invariant regular foliations of the phase space, and you have canonical transformations that trivialize this.
Can you explicitly write the H3, H4, and so on?
Yes. Yeah. And I also write those later using another method. Okay. Yeah. So I present three methods, and I'll use one explicitly. Okay. All right. Okay, so the infinite dimensional version of the transformation to action angle variables is called the inverse scattering transform. And it's based on the fact that KDV can be seen as the compatibility condition for this auxiliary linear system here. So psi here is a vector, u and v are defined as such, and small u here is potential, and lambda is an arbitrary constant called the spectral parameter. And what I mean by KDV is the compatibility condition for this problem is that if I write the cross derivatives of psi and impose that they should be equal, then I end up with this relation here, which importantly doesn't depend on lambda at all. And also it is satisfied provided the potential satisfies KDV. Okay, so KDV really is the compatibility condition for this auxiliary linear problem. Okay. And here the name zero-curvature representation comes from the fact that these two equations, they can be seen as defining a connection, right? Or a gauge field, if you prefer, over a 2D vector bundle over the xt plane. And so this first equation here, it tells you how to parallel translate psi along the x direction and this one along the t direction. And this equation here can be also seen as the curvature or the strength field, if you prefer, of your connection via the Ambrose-Singer theorem. So based on this interpretation, we can also define the parallel transport omega along a curve gamma in the xt plane as such, where the p here means path ordering, right? And so we can use this also to transport psi. So say your curve gamma goes from ys to xt, then it means that psi of xt is just omega gamma psi of ys. Right?
This means that just omega satisfies the first order differential.
Yeah, exactly. Yeah. So yeah, see, it says here and here. Yeah. Okay, so this also provides a more geometric approach to integral systems. Okay. But this zero-curvature representation can also be used as a way to generate the conservation laws. So to do so, let me introduce the two transfer matrix T and S, which are just a parallel transport along X and T. Okay. And then the zero-curvature condition, it implies via the non-Abelian-Stokes theorem that the parallel transport along a closed loop should be the identity, and which is in particular the case for this rectangular loop gamma R. And then if the potential U, so the solution to KdV is periodic, I can write this relation for the time transfer matrix from just exchanging the bounds here of the integral. And if this is true, then that means that this identity implies that the space transfer matrix at time t is related to the space transfer matrix at times s only to a rotation. Okay. So that means that its trace is conserved, and we can use this trace as a generating function for the time conserved quantities by expanding in terms of lambda. And in a similar way, we can use the trace of the time transfer matrix to generate the space conserved currents in the same way. Okay, right. So this structure is very general when it comes to integrable systems. It's not restricted to KdV at all. And it's also as a basis, as I said earlier, of the inverse catchment trap. Okay. So here in this slide, I will just give you a rough sketch of what the, yes.
So it's generally understand that there are no counterexample classical integrable models where there is no the zero curvature which phrasing.
Yeah, I don't know any of this. Yeah, okay, I don't know it. Yeah. So yeah, here I'll present a rough sketch. Later, I'll show you how to do inverse scattering transform in the special case of what's called finite gap theory. But I still wanted to provide you with the general procedure. And the idea is that you start with your initial condition for KdV, so u of x at t equals 0, and you use it to initialize your auxiliary problem. So you start with small u, you use it to get big U, the x part of the connection, and from that you can compute the transfer matrix. And then because of the zero-curvature relation, you know how to evolve U, it depends on V, right? And from that you can also find how the transfer matrix evolves, so it satisfies this equation. Yeah. Then once you've successfully managed to evolve T, you can then inverse the transform and from T obtain U. So you can see this as some sort of nonlinear Fourier transform. And in fact, if you put a parameter in front of the KdV nonlinearity and send this parameter to 0, this inverse scattering transform just becomes a Fourier transform. Okay. So here, of course, the hardest part is to inverse the transform to get the KdV wave field from the transfer matrix. But to be clear, nothing here of this is really trivial, and so that's why I won't go into the details of the general case. Instead,
that you go from U0 to tau 0 with IST, maybe just scattering problem.
yes, exactly. So I will
In the university, so
yeah. So
I would change.
Okay. Yeah, okay, I see what you mean. But yeah, I'll show the spectral scattering problem.
It's called direct.
Yeah. Yes.
Start from potential, you find scattering.
Yeah.
Maybe evolution and go by inverse.
Exactly. Yeah. I put a IST -1. Yeah, sure. Yes. So the next I will show you how to construct two types of solutions. So using again, two new representations that are more specific and more convenient to study these kind of solutions. Well, now we'll start zooming in a bit more. So I'll start with this one, which is called the lax representation. So the zero curvature representation is very general, but some equations like KdV also have lax representation like that. And the general idea is essentially the same, is that you write KdV as a compatibility condition, again, for an overdetermined system, but this one, a scalar system equation, okay? And here, L and M are typically called the lax pair. L is often referred to as the lax operator. And those two operators satisfy the lax equation here, which is the compatibility condition for those two equations. And this compatibility condition is satisfied, again, provided that U satisfies KdV and that the spectral parameter is a constant. So yes, that's the general idea. And
So what is the general idea of how to guess the lax pair? Just
okay. You have to guess.
really, there is no aggressive.
Okay, so
Just experience helps.
yeah, experience helps. You have some methods that involve Lie groups. Okay, but yeah,
But better,
right.
learn an example.
Yeah, exactly.
Okay, I should
Yeah, good, exactly. And the thing is, so any system that has a lax representation also has a zero curvature representation. So here, for example, if you take psi and to be phi x, yeah. If you write which equation psi should satisfy using the relations, you directly end up with a zero curvature. So what we are doing here is just taking an additional property of KdV to simplify the auxiliary problem and make the inverse Kaplan transform easier to perform. Okay. So as I said earlier, the idea is that you start with your initial condition ux of at t equals 0, and this specifies phi through this linear spectral scattering problem. And then you can evolve the scattering. You can evolve phi using the second equation with this m here. So I'll start by talking a little bit about the scattering problem here. So
you're starting the problem is periodic boundary conditions.
Yes, yeah, exactly.
More complex.
So here the lax operator is a Sturm-Liouville operator. So you can see also this equation just as a stationary Schrödinger equation with arbitrary periodic potential, right? And the spectral theory of this kind of operator is very well known, so I will tell you a little bit about that. But first, I need to say that it's often convenient to write the solution of this kind of equation as a linear combination of two basis solution, phi plus and phi minus, that I fix by fixing the value at x naught. Okay. Yes.
So this lax representation, so it kind of means, so when this phi evolves in time, then it stays in this, like in this eigenspace of L. Right, so this L defines, so the L phi is equal to lambda phi.
L phi is equal to, yes.
So this means the phi is in some eigenspace of the L.
Yes. Yeah.
And
it's
then
the exact function.
The time evolution just lets it stays in the
Yeah, you stay in. Yeah. And that works because you have this compatibility condition here.
And so is the eigenspace like is it one dimensional or is it dimensional?
Yeah.
Given lambda, yes, but
With position.
yeah. But you see the you'll see how the different spectrum later, but you have infinite values of lambda that are.
Yeah, of course, yeah. Yeah, okay. Thanks.
Okay. So yeah, just one thing also about this basis solution. So there are complex conjugates if the wave field and the spectral parameter are real, which will be the case here. And there's something also you can see if you take, for example, lambda to infinity or equivalently due to zero, you will see that the two basis solutions are just two plane waves moving in the opposite direction. Simple. Okay. So because the potential U is periodic, this implies that the scattering problem is invariant with respect to translation by, okay, and that we can write phi plus and phi minus at x plus L in terms of phi plus and phi minus through this monodromy operator T. Yeah. I've called it T because it's related to the transfer matrix from before, the zero-curvature representation. And as you can see here, there's already a lot of structure in T. This A star, B star. And that's because phi and phi plus and phi minus are complex conjugates.
Just you, periodicity condition was somehow dictated by something, or it was just your choice? Just your choice.
When the initial conditions set period.
Yeah, so
okay.
Yeah.
Just this plus or something.
yeah. And why I'm doing that is because the Busky and Kruskal did that, and
Okay.
and PUT did that.
They did the decay condition.
As they did both, but the first paper in 65
It's the first paper, yes.
no.
Then the periodic, it was numerical function, it was later.
Oh no! I mean the numerical solutions. Yeah. No, of course the IST. It's
Then you use the scattering, inverse scattering, which is typical.
Okay.
Yeah.
Sorry for.
Yeah, no
Just
worries.
wanted to understand whether there is deep truth in there, so just choice.
It's a choice of.
yeah, it is a choice.
Okay.
Yeah.
Mhm.
Okay. Right.
Still is not true.
There's both.
I would say, is it this the easiest example of which to understand or not? Basically, the question. Yeah.
It's if it's not the easiest, it's the second easiest.
Okay.
Because I can think of another one, but right, yeah. Okay. And so this monodromy operator, it has some nice properties. So first, it's unimodular. That's something you can see because the Wronskian of phi plus and phi minus is a constant. And also because of this A star, you can see that the trace is real. Okay. And you can use those two relations to write the eigenvalues of T in terms of the real part of the A coefficient. Okay. Where I've introduced here this pseudo momentum P. So if you do that, that means you can also write the trace of T in terms of the sum of those two eigenvalues. But since you know that it must be real, that means that P has to be real, and also that the real part of A has to be between -1 and 1. Okay. So in fact, this condition really constrains what values of lambda you can take. Okay, so the spectrum is composed of bands where P is real and of forbidden gaps where it is not. Okay, and in general, for arbitrary periodic potentials, your spectrum contains an infinite number of bands and gaps. But if U is also a solution to the KdV equation, then it may contain only a finite amount of bands.
What is P again?
P it's just defined like that. So this is the value of T and
The reference Kamchatka 2000s.
Yeah.
Is a reference for what?
For the figure. For the figure.
Look, it's Kaplanov. It's 100 years before.
Okay, yes, this one I took it from this book, but yeah, okay, yeah. I can
He cited level.
I can do. Yes.
Okay.
So yeah, that's the idea. So for if U is a solution to KDV, you can have only a finite number of gaps. So those potentials, they are called finite gap potentials, and the framework to study those is called the finite gap theory. Okay. So indeed, here you have an example of that I took from Kirchhoff's book, which is older than that. So it corresponds to the spectrum for a specific U, where there are 4 bands. You have lambda 1, lambda 2, lambda 3, lambda 4, lambda 5, lambda 6, and you have one single semi-infinite band, lambda 7 plus infinity. Okay, so the potential U completely specifies the band structure of the spectrum, but you can also approach the problem from a different angle and ask yourself, given a specific band structure, what should be U? Okay, so that's what we'll be doing now. So the simplest example of solution, of non-trivial solution, corresponds to 2 bands. And that's because if you take only a single semi-infinite band, it corresponds to a constant U. So that's not very interesting. But as you will see, even for this simple case, the way to obtain the weight field U is a bit convoluted, right? So the next few slides will be a bit technical, but I think it's still interesting to show you how inverse scattering works. So please bear with me for this. Okay. So I'll start by recalling my linear auxiliary problem, and again, I can write a solution in terms of a linear combination of phi plus and phi minus. And here, with that, I can introduce a so-called squared eigenfunction G as just the product of phi plus and phi minus, and I can write equations for it. And what's interesting here is that, as you can see, the first equation G solves is a conservation equation, which means that G is conserved, and we can use it again as a generating function for the conserved quantities. So the way you do that is you take G, you expand in terms of lambda, all those GNs are conserved as well, and you use the second equation to set up a recursion relation, and then you generate all the conserved densities that way. Okay. But that's not the only thing you can do with the second equation. You can take it, you can integrate it with respect to x, and you end up with this new equation here, where the integration constant here, generically it depends on t, but here we've imposed that lambda is a constant and that the spectrum only has 2 bands.
Why can you go up?
Yes.
So why is the question of conservation equation?
So you have fx equal to ft equal to x. Yeah, you have density current.
Okay.
Yeah, x and t derivation. Yes.
So what do you
Yeah.
integrate over? The second equation.
Yes, this one you integrate it over x, and you get that. And this integration constant generally depends on t, but because we impose that lambda is a constant and that the band is only composed, the spectrum is only composed of 2 bands. Sorry, the consistency it's a bit tedious to show, but consistency imposes that R has this structure here. And more generally,
And these lambdas are exactly these lambdas.
yes, these are exactly these lambdas. So, yeah, exactly. And more generally, finite gap theory, it identifies periodic solutions to the KDV equations with a Riemann surface that is characterized by this polynomial R, which roots are just the endpoints of the spectral bands. Okay. Right. And here, as you can see, you have degree 3 polynomial in lambda. Here you have g squared times lambda. So we look for solution in terms of a degree 1 polynomial in lambda involving a function of xt mu. That's called typically the auxiliary or Dirichlet spectrum. And you can write equations for this again. They look like that. But what's really important there is that if you only keep terms of order 2 in lambda, what you get is finally a way to relate the KDB wave field to the solution of the auxiliary problem. Okay. And now what remains is only to solve these equations for mu. Right. But the way to do it is a bit tricky. It's just you can get rid of the potential u by setting the value of the arbitrary spectral parameter to be equal to mu. And you can do it for.
But that means zero will be g will be 0. Lambda equals mu.
G will be 0, yes. G will be 0, but you're solving for mu because you want u with u depending on
This
this.
very special choice of g, right?
Yes.
Not clear to me.
So exactly how they came up with.
So the idea is that one should look for g equals 0.
Yeah.
Of that, or because g
Of
is
that, yeah.
g equals 0. So
But lambda equals 1.
for x of plane x of t.
Why yes. And if you do this, this previous system really simplifies to this one, where here I've simplified this by using the relation between u and mu that I just showed you before. And already, even if before I start looking how to solve this, I think there's already something interesting here. The fact that mu has to be real. So it means that mu must be between lambda 2 and lambda 3. So that because this is where the polynomial R is negative, right? And so that's where the name auxiliary spectrum comes from. It's because mu lives within the spectral gap. Okay. But then you can also realize that mu t is proportional to mu x. And so you can solve this system by introducing a new variable xi, and you reduce the system equation to a single ODE, this one. And this you can integrate, and finally you end up with a cnoidal wave solution, which takes this name because of the Jacobi elliptic Cn function thing. Okay, so if you want to study problems where you have a large number of bands, you can apply more or less the same procedure by changing R accordingly. And it's a bit more complicated, but ultimately you end up with a rather compact expression that involves.
Then you need to integrate something 1 over square root of normal of
exactly.
Which is not elliptic function.
No, it's Riemann theta function.
It's Riemann theta.
Yeah.
Yes.
So
it will be expressed in.
Yes. So in the end, you get something expressed in Riemann theta functions. Yeah.
Okay.
Right.
I start remembering some lectures and feature there. Okay.
So the free spectral parameter I thought was independent of x and t.
Yes.
Now you put it as function of x and t.
So yeah, I agree. This part of the procedure has always been a bit mysterious to me.
Mysterious.
So yeah, it works.
A lot looks mysterious, but obviously works. So
you
understand.
So all of the rest, I can really follow the problem. This I'm not completely sure, but yeah, in the end it works. Yeah.
I'm a bit confused. So, like, if you say lambda equal to mu of xt, why do you still have an equation for mu? Like, mu should be just lambda.
Right. No, it's you have this, and the idea is you kill this term, for example. And but it's equal to lambda, but you don't know what lambda is. So
But so now lambda can depend on time or.
yeah, so that was a Benjamin question, and that's the thing I think is a bit mysterious. Yeah. But yeah, when I look at various references like the book of Chatnoff or the book of Ellen Hofer on the subject, the all just say that with no explanation. Okay.
Yes,
Yeah.
the recipe, right?
Yeah.
The points in this way.
It's not.
Yeah, no, but that's why I understand. I understand.
Not your fault, definitely, but it's just. I hope that after 40 years or more than 40 years working with this, people already learned some educated way of which avoids guessing.
Yeah, no, but there are other ways, right?
Yes, there are other ways.
Ah, there are other ways.
There are other ways. There are ways.
Let's guess work.
Yeah, less guesswork. Like if you start with the zero curvature condition, you have less guesswork, but it's a bit heavier.
Okay.
Yeah. So
Okay.
More transparent picture if you spectral theory Schrödinger equation.
yeah,
But here it's a bit artificial.
yeah. No, I agree.
It seems like that.
Okay.
For general case, there is complete solution of those problems, and you can easily pass to these analogs of variables action and angle.
Yeah.
Yeah.
Okay, but it's still very useful
Yes.
to have a look.
Be more direct.
Yes.
The problem is that these lambdas, they roughly speaking, they're edges of the gaps, and they are not independent parameters, and you have to change something.
It's
For these equations, you have to have independent parameters like action and.
Okay. Good.
all right.
So if you claim this is the simplest example, I should.
Yeah. The thing is, so the other example I know using the zero curvature representation, it's there's no guesswork here, but it's longer and it's
No, fine, yeah. Thank you.
For solitary solutions, line, I guess it's specific.
yeah, okay, for solitary.
Form.
Right. So yeah, it's easier in some ways. The thing is, the formalism with zero curvature solution needs to be introduced.
Yes.
And,
Okay.
and this one is big.
Let's go on.
Yeah.
So basically, if I understand correctly, what you do is you kind of choose any spectrum on the linear line, like you're showing right on the first step, and then you try to find the 10 features.
And you find you.
Is it possible to like avoid that the spectrum goes all the way to infinity? Like if I just take a single band in like lambda 1, lambda 2.
No, constant is lambda 1, lambda infinity. So just so the thing is that I'm sure that it will be solution to KDV. So and yeah, I'm pretty sure it is not because the finite gap potential solutions to KDV always involve this semi-infinite band.
So like. So it's not the case that I can just write down any spectrum and then whatever comes out will be the solution to KDV.
No. So it's like KDV has a particular bound structure of the spectrum, and you use it to get it. But all spectrum are not equivalent to KDV solution.
What do the other solutions? Are they solving any equation, or is it just they're just there?
They're just there. I mean, you can probably find an equation for it for them, but yeah, I don't know. Okay, so this cnoidal wave solution, its wavelength depends on this parameter m. Yes, that's here and there. And as you can see from this definition, it means that it depends on the finite band. If the finite band is large, m is close to 0, and if the finite band is small, then m tends to 1, as lambda 1 approaches lambda 2. And so I've put a smaller animation here to show you how it goes. So I start with a large band, so my wavelength is rather small, and then I take lambda and I take it closer and closer to lambda 2. And eventually, when lambda 1 is equal to lambda 2, the wavelength becomes infinite, and we end up with a soliton. Okay. So solitons, they can be seen as canonical waves, but in the limit of infinite wavelengths. Yeah, exactly. And if you take this this expression in this limit, then you end up with this expression which is indeed a soliton. And here, lambda 3, so the endpoint of the semi-infinite band, it essentially corresponds to a background, right? And so, as we said earlier, so if you have just one semi-infinite band, you have a constant solution, and then here you are adding a single point of a discrete spectrum, which corresponds to a soliton that moves then on top of this background. Okay. So since it doesn't add too much, by convention, usually we set lambda 3 to 0, and we end up with the usual one soliton solution of KdV. So again, this is a localized pulse, which velocity is positive and proportional to its amplitude. And this is all completely specified by this parameter eta, which is directly related to the value of the point of the discrete spectrum. Okay. So usually it's more convenient to work with eta rather than lambda. So when I'll be talking about spectral parameters, starting from now, I'll be referring to eta. Okay. Okay, and so do we want to make a break at some time? Or because we could have done it earlier.
Yeah, I think now it's probably
Okay.
better just to.
Sure. All right. Okay, so the last few slides will be dedicated to solitons specifically, and how to construct solutions to the KdV equations that involve n interacting solitons. Okay. And the first thing we need to ask is why should we study solitons where they are just infinite limit, wavelength limit of canonical groups? And there are three reasons for that. So the first one is purely practical, and it's because they are easier to handle than multi-phase solution, multi-phase finite gap solutions. Yeah. The second reason is that solitons have some interesting particle-like behavior, and so it will be easier to make parallels with statistical mechanics using solitons. And finally, maybe the most relevant reason is that any finite gap solution can be very well approximated by an n-soliton solution, provided that the number of solitons is large enough. Yes?
These statements are not sure to keep KdV.
Okay, is this more general? It's not only for KdV. Probably it works for NLS as well. But if you take an integral system like the three-wave model, for example, it doesn't work. Yeah. Yeah. And here, since the idea ultimately will be to study the statistical properties of the KdV solution for random initial condition, then it will be easier to work with the basis solutions. We have more control on the n-soliton solutions. And here, to illustrate this, I put on the left, there's a canonical wave solution in black, which is superposed to an n-soliton solution in red. And on the right, you have the absolute error between those two solutions for 50, 100, and 200 solitons. So you see that they agree very well. Of course, the cnoidal wave solution is defined on the whole line, whereas the N-soliton solution has finite support. But so that means that they will agree only on a domain of finite size, but the size of this domain increases as you increase the number of solitons.
So for your solitons are always finite energy.
Yes, a single solution has finite energy. Yeah. And in fact, there's also some recent rigorous results by Bob Jenkins on the convergence of N-soliton solutions towards finite gap solutions. And unfortunately, it's not published yet, but I talked with Bob last week. He told me that he expects to finish the paper and put it on archive by the end of January. So I don't cite it because there's nothing to cite yet. All right, but the main idea here, to give you an idea of that, is you take your band spectrum, and instead of having continuous spectrum, you take the bands and you populate them densely with several points of discrete spectral data. And so you can do this, and to be accurate, you need to populate those bands densely, but according to a very specific distribution of spectral parameters. And that's something that I will be discussing next time.
You mean not uniform?
No,
but in some particular.
Yeah. Uniform.
Uniform won't converge. Or converge very slowly.
Or converge very slowly, or converge to something that's not a cnoidal wave, but at yes.
So here you have a good approximation, but as time evolves, this approximation.
Okay, yes, that's part of the results of in Bob's paper. It's the this approximation remains good on some domain. That's on some spatial domains that depends on the number of solitons.
And then it remains good forever.
No, not forever. You also have a time horizon for the size of the domain becomes smaller and smaller as time goes on, but this is related to the number of solitons. Yeah. Yes.
Just for curiosity, so the distribution is a simple one or very?
It depends.
Okay. So next.
Yeah, next time. So for the cnoidal wave, it involves the ratios of elliptic functions. But for simpler things like what they call typically the cnoidal condensate, where you have just the semi-infinite band, where the solution is then just a constant. You can create a constant by just putting solitons at the right place. And then the spectral distribution is basically it's a derivative of the semi-circle. But then all right. Okay, so the last formalism I want to introduce is tau function formalism. So and this is, I think, the most convenient way to construct N-soliton solution. And so the tau function was introduced by Hirota. So he didn't call it like that at the time, but it was introduced in his paper in yeah, kind of. Yeah, kind of. Exactly. Yeah, it's very close to Kolov in idea. So yeah, it was introduced in 71, and basically it's a change of variable to solve KdV, and the wave field is just a second derivative of the log of the tau function. And if you put this tau function and you input it in KdV, you end up what's known as Hirota's bilinear equation, which is given in terms of the so-called Hirota's T operator. Okay. So like that, it looks a bit complicated, but Hirota in his first paper he proposed a solution to this equation in this form.
What is dot stands for what?
Yeah,
Just acting on.
acting on.
Okay.
Yeah, like this.
Okay, just definition.
Yeah, it's just definition. Yeah.
Mhm.
Yeah. So, on a side note, I don't really recommend this paper by Rota, because it's less than 2 pages long and it's barely explained. But he wrote a book 30 years later, which is much better. So, if you want to read something, read the book. But yeah, so in his original paper, he proposed this form of solution, where this symbol here is, it means you're summing over all combination of small n elements taken from big N. And it involves here thetas, which are the phases of your solutions. And this A, which can be expressed as a product, or involving phi here, which can be interpreted as the scattering shifts the solution incurs as they interact. Okay. So this change of variable involving the log and this form here, it was inspired to Hirota by a paper by Kay and Moses, in which they studied a very particular type of spectral data for the Sturm movie operator, composed only of discrete points. That's why this original tau function only works for solutions. So Hirota knew about it. He had recently been interested in KDV because he read the then new paper by Gardner and collaborators on the inverse scattering transform. He took this tau function originally as a clever calculational tool, and even though he knew about the inverse scattering transform, the precise connection between the tau function and inverse scattering was not yet clear. And also, as I said, this at first was only working for solid solution, but then it's been recontextualized and extended to account for more general solutions. And the first big step forward in the theory of the tau function came from Satsuma in 1979, where he showed that you could write the tau function in terms of a Wronskian involving linearly independent solutions of the auxiliary linear problem in the lattice representation. So originally he did this just to give a new interpretation of the tau function for the n-soliton tau function of Hirota. But this form is in fact more general, and people realize later that if you take linearly independent solutions for an appropriate band spectrum, you can generate finite gap solutions involving n bands and or points using this. Yes.
So this L contains the U, right?
Yes.
This is the solution to the KU.
Yeah.
So can you put solutions of different lambdas in there, or?
Can you put different? So you specify your spectral problem. So you specify a band spectrum, and you look for which solutions satisfy your spectral scattering. What are the eigenfunctions?
I think so.
Because you have the same spectrum for all the Fs.
But so if I would like to construct this determinant, right?
Yes.
Then I would need first the solution to the KDV equation.
Yeah, but that's the trick. Since you know that you directly specify the spectrum, you choose a band spectrum structure, and then you look for the solutions of the scattering problem associated with the spectrum. So you don't use U explicitly at any point. Yes, right. So the last two interpretations for the tau function I want to mention Those are things I'm not too familiar with, but and that's something I want to delve deeper into, but not at the time yet to do so. But I think it's still interesting to mention them because maybe some of you are familiar with this. And the first one is called Sato theory. It was developed in 81 by Michio Sato. It was first developed to tackle the KP equation, column set specialty, which is a 2D version of KDV, still integrable. And from what I understand, Sato theory is completely massive. I mean, it's been extensively developed since its inception, but the basic idea is to consider KDV as generating the motion of a point on a Grassmannian manifold, and to see the Hirota's bi-Hamiltonian equation as a spherical relation. Then you use this additional structure to get information on your solutions. And the last thing I want to mention is the fact that tau functions are often said to be partition functions for the eigenvalues of random matrices. And that's something that's discussed, for example, by von Merbecker in his 2000 paper, where he relates KDV to ensembles of infinite Hermitian matrices.
People work on this.
Yeah. So if you're familiar with that,
No, I just want to say what the question was here. So there is some crowd of people working.
yeah, okay.
From the world.
All right.
Fine now. I get hate pain. If this cut in one forever.
Oh,
Okay, no.
I don't
I will. Okay, well,
Thank you.
they exploit it very efficiently to calculate some matrix integral.
Yeah. All right. So the last formulation I want to show you is this one, which I think is the most convenient one to compute N-Sullivan solutions. And it just corresponds to taking Hirota's first formulation, but writing it as a determinant of a matrix. Okay. So here M is a symmetric n by n matrix, n being the number of solitons, and it involves the spectral parameters of your solitons and the frequencies which are recorded here. So maybe that's another problem, nice problem of random matrix theories, like how to get tau for large n when you distribute randomly the etas and the x naughts. So yeah, so that's probably. I don't know how to do this, but if you have any ideas, I'm interested. And yeah, so starting from that, it's pretty easy to recover the one certain solution we got from final cut theory. And so recall that the wave field is just the second derivative of the log of tau. For n equal to 1, tau takes this very simple expression, and you directly recover the usual expression for the KDV soliton. And then again, this corresponds to a single pulse moving at constant speed proportional to its amplitude without ever changing. Okay.
Do you have nice expressions for the conserved densities without motion?
From the tau function. A way to get them systematically, and I don't know actually. Okay, so now to study how solitons interact, it's useful to first look at the two soliton solution. So I've written it here. So already you can see that it's a bit more complicated, but in fact, when you plot it, you can see that what actually happens is very simple. So you start with two solitons far away from each other. It looks like U2 is in fact just a superposition of two one-soliton solutions. Then they come closer to each other. They start to interact non-linearly. It almost looks like that they switch places, or like the big one takes the small one and throws it away to get some a small boost, and then they separate again. we cover the initial shape, velocity, and size. Okay, and that's something
These etas, can you choose them as you want? Or the constraints?
they need to be positive. Yeah, they need to be positive if you want to have zero background.
If the back is not positive, you can choose them.
Yeah, no problem. Yeah. And yeah, this behavior you can see from this video. That's something you can also see from the long-time asymptotics of this expression. So if, for example, we assume that eta 1 is bigger than eta 2, so that soliton 1 is faster than soliton 2, then we can look into the vicinity of x equal 4 eta 1 squared t as t goes to minus infinity. So this corresponds to focusing on the first soliton well before the interactions. And then if you do this, the phase of the first soliton theta 1 stays finite, whereas the phase of the second soliton goes to minus infinity. And then this expression here reduces to this one, which is just one soliton solution. But instead, if you still look at in the vicinity of x equal 4 eta 1 squared t, but as t this time goes to plus infinity, then the theta 1 still stays finite, but theta 2 goes to plus infinity then. And this reduces to that, and which yield again one soliton solution, but this time the solution has picked up a shape. Yeah. And this scattering shift depends on the spectral parameter of the two interacting solitons. And the bigger soliton gets shifted forward, whereas if you do the same kind of long-time asymptotics with a smaller one, you'll see that it gets shifted backward. Okay. So to illustrate that again, I'll show you again the same solution, but I've superposed on it also two one soliton solution. So you see that they agree very well at first, and then they interact, and after the interaction, they stop agreeing. And the difference in position here is just scattering shift. Right. So you can do the same kind of asymptotic analysis for n-soliton solution in general. And for very large times, solitons separate, and you can approximate your n-soliton solution by a linear superposition of n one-soliton solution. And from this, you can already see that the scattering is in fact elastic, because at t equal plus infinity, you have the same solitons as at t minus infinity. The only thing that changed is the initial phase here, x plus or minus, which are typically called the impact parameters, and they represent the position at t equals 0 of the soliton if it did not interact with the others, and this superposition could hold at all time. But I need to stress still that this is not, in fact, the actual position of the soliton at t equals 0. Right? First, because between minus infinity and 0, you might have encountered other solitons and picked up shifts, but also because when solitons are interacting, they essentially delocalize, and you cannot say where they are. It's some blob of solitons.
But asymptotically you can.
But asymptotically you can. Yes. Okay. So each the set of the pairs of impact and spectral parameter, they completely specify your n-soliton solution at all time. And as you can see, the etas are constant in time, then the position only evolves linearly. So you can see those two as action angle coordinates for your system. And in fact, the scattering map that takes your n-soliton solution at finite time and then gives you its long-time asymptotics in terms of a linear combination of one soliton solution, this map is canonical. And in a way, you can asymptotically map your n-soliton solution to a system of n free particles. And this will serve as the basis of our statistical mechanics and generalized dynamics approach to KDV that I will be discussing next time. So what's the last thing I want to say about this is that we can relate the plus and minus impact parameter in a very simple way. So the difference is just the sum of all the scattering shifts as the soliton interacts with all the others. So asymptotically, it looks like
They're pairwise.
yeah, pairwise, yeah. So asymptotically, it looks like it's pairwise. So if you look at the field during the interaction, this is not the case. It's more complicated than pairwise. But asymptotically, it is. The long-time results are factorizable. And the last thing here is that you can see there's a sign here. So that's because, as I said, bigger solitons are shifted forward and slower solitons are shifted backward. So in effect, you can consider that solitons are repelling each other. Okay, and that will be an important thing for next time. Okay, so I want to conclude my lecture by showing you an example of a soliton solution of KDV. So this is a 100 soliton solution of KDV, and you can see that the structure can be extremely complex. This field is completely erratic. And so this, along with the inherent complexity of many real wave phenomena, it naturally calls for a statistical description, right? Okay, so that's what I will be discussing next time, the statistical mechanics of a gas of soliton. Yes. And with it, yeah, this reference, and thank you for attention.
Can I ask you again, like, from this tau function presentation,
Right.
like the determinant of the function, right?
Yes.
So if you go one slide ahead, then you write on this answer, right?
Yeah. Okay. So going from this to that, it's not direct.
Yes.
Yeah.
So it doesn't. But so can you write like any soliton solution in this form? Or?
Yes. Yes.
Okay, but this is highly non-trivial.
Yeah, it's highly non-trivial, and if you want to say write finite gap solution, it will not take this form at all. Even if you change the phase to account for that.
But the claim is the determinant approach something which will approximate.
Yeah. No, this is exact. I mean.
No, I mean,
Yeah.
you'd like to approximate by soliton solution your.
Yeah.
Finite gap, then
Next time, yeah, I want to do this. Yeah.
So, I think there is a theory on more, and correct me, but so is the claim that any initial state will at the time asymptotics will be an soliton solution with perfect shockwave or for KDV, or it's not?
It would be if you have finite support. So that's the tricky part. And the soliton gas approach, one of its appeal is that you're taking the limit n goes to infinity. So you're generating also a solution of infinite support.
But
So yeah, it's
sorry, so just another question. So if I have a unrelated shockwave,
Yes.
so in the spectral space, what does it correspond to?
dispersive shockwave. Okay, typically it's you will have like two. Okay. Way you can see it is it's an inhomogeneous solution. Okay. Yeah. So that's the thing. So where you can do this is like for example, Gennady in the paper where I picked the picture where the octoidal waves proposed, they look into they do a dispersive shockwave, and the way they do this is that they start with just one band problem between 0 and L. And after L, it's also one band problem, but with a different endpoint. So you have two constants of different size, and then you have the dispensation constants.
All right, let's see for the questions. We have one talk left on Wednesday, which is the last one of this year. Yeah, no, Charles is already here today, no? Or is he coming later?
It's coming later.
He's coming later.
So continuation of this,
Yeah, your next lecture is mid-January?
Yeah, it's the 20th.
20,
Yeah.
something like that. Yes. Yeah, and then we start the new year, I believe, on the 10th of January.
that is the seminar.
Yes, that's the first seminar by Mohammed Osman.
By Mohammed, yes, okay, okay.
I think that's.
Yeah, keep it in mind.
They should be announced.
Will we?
Yeah, yes.
And then next one will be on 25th, right, by, or
There's one month.
No, there are more before.